In every programming journey, there comes a point where the programmer decides to finally sit down and study. Few programmers get really good at it. Some programmers simply survives it, but most die trying to understand it. So I'm going to spend the next 7 days studying the 7 basic data structures, and I'll be solving one lead code problem for each data structure. Am I going to conquer it and thrive to finally land my $500 billion a month tech job? Or am I going to lose my mind trying to unravel the mystery behind data structures? Before we can move on to the first data structure, what even are data structures? Programmers deal with massive amounts of data every single day. So the way that we came up with to store these data was creating certain structures to store data, or as we would call it. Data structures is so important for programming, it literally exists everywhere. Your friend list on social media, data structures. Slightly funny Twitter threads, data structures. Even Mother Nature herself, data structures. Secondly, in a career sense, if you want to ever land a job in big tech companies like Google and Microsoft, within the interview process, they'll always ask you questions relating to data structures. As you'll see throughout this video, each data structure possesses some unique property that builds off of a certain advantage or disadvantage from a previous data structure, all with one main goal in mind: to determine the fastest way and most efficient way we can process data. We can start with a basic variable which stores one data or element. Through this variable, you can basically access and retrieve the element and do whatever you want with it. But on the internet, we deal with millions amounts of data. Not a single soul is going to sit in his office declaring variables all day. That's 2 username done. Only 5 billion more to go. I paid a degree for this shit. So the simplest solution to work around this is using the first data structure that we're going to study, which are arrays. One array can store multiple different elements or data contiguously, which is an important thing we'll get back to in just a second. Each data or element in the array is given a number starting from 0 to however much data there are, and this number is referred to as the index. The way to which you can retrieve, access, and use these elements or data from the array is by using the index. To study for data structures, I would start by going online looking for online resources and then taking notes of important concepts. There were 4 main things that I looked out for: what the data structure is, time and space complexity, advantages and disadvantages, how you're going to implement them, what are the different variations. I'll also study in space increments of 25 minutes, which means that I'll study for 25 minutes, take a 5-minute break. After I've done that 4 times, I'll take a 15 minutes break. The first lead code problem that I'll be trying to solve is called toSum, where you're given an array of integers and you're also given a number called the target, and the goal is basically to just look for 2 elements that will add up together to give you the target, and then you want to return the index of those 2 elements. To solve this problem, I started with a simple for loop to allow us to traverse through the array, and then I nested another for loop inside. Every time I would try and compare the element at the current index to the element next to it, and then add them up and store that into sum. If sum is equal to the target, then we want to just return the index of those 2 elements. But if it's not equal, then we want to reset sum to 0 and then move on to the next element. You can also start with breaking the main problem down into tinier problems. You can start with a problem of just finding a way to move through the array and then finding a way to track the sum of the 2 elements. Solving these tiny problems would help you to solve the bigger overall problem. After I was done pseudocoding, I wrote down the actual code, click submit, and we were done with our first lead code problem out of the 7 that we're going to try and solve. Remember when I told you arrays store data contiguously? Well, this means that it stores data back to back. Let's say you want to add an existing element. The program will have to look through the entire computer's memory to find slots that are enough to fill all the elements currently in the array, and this is extremely inefficient. The next data structure that we're covering actually tackles this problem in a very interesting way. But before we can move on to that, here are my final rankings for arrays. 3 out of 10 for difficulty. They are the easiest data structure out of the 7 we'll study. I'll give arrays a 10 out of 10 for coolness. They're sort of like LeBron James. And then lastly, I'll give them a 7 out of 10 for efficiency. They're not the most inefficient things, but there are definitely areas to improve upon. Let's move on to the next data structure. Yo guys, did you just see that? It's like some sort of lists that are all linked together. The biggest problem that we have currently is the fact that data needs to be stored back to back, which makes inserting and deleting elements extremely inefficient. The simplest solution to get around this is just to store data randomly throughout the computer's memory. Does this mean we'll have to search through the entire computer's memory every single time to look for the element that we want? Well, this is where linked lists come in. Linked lists are basically like trains. You know, you have tinier trains which are called the nodes. You also have a starting train, which is called the head. And then you also have the final compartment in the train, which is called the tail. I would say it's an easy concept to wrap around. The true difficulty comes from when you try to sit down and implement your own linked list. I was sitting there not knowing anything after I thought I had a pretty good understanding of what linked lists are. But once I was able to actually implement them, that's when I actually started to understand them. Now you might be thinking, how do linked lists actually solve the problem that I mentioned just now? Well, this is where the interesting part lies. Within the node, you have the data itself that you're storing, but you also have something called a pointer. What this does is it basically tells the program where the next data is located. And that way, you don't have to search through the entire computer's memory. You simply have to access the pointer, and that leads you directly to the next data. While being very efficient in allowing you to insert and delete things, it also comes with a cost. In order to access elements, you have to start from the head and move all the way down the linked list until you find the element you want. And that can be considered pretty inefficient. The problem I had to solve for linked list was a relatively common problem, which is to reverse a linked list. I was given the head and then I had to reverse the linked list physically and then return the reverse output. I have implemented a linked list before, but I've never tried reversing one. So this was my first time going through it, and it was honestly really hard. The basic logic to reversing a linked list is you just need to change the pointer of the current linked list to point to the element before it. But in order to achieve that, you need to first iterate through the linked list. So then I started off with creating a simple function that'll allow me to move through the linked lists. Afterwards, I needed to keep track of the previous node, the node before the current node, the node that was next, and I need to keep track of the current node. Every time I would go through a node, I would set a variable to store the next node. I would set the pointer of the current node to the previous node, and then I set the previous node to the current node, and then I set the current node back to the variable that originally stored the next node. And that's basically how you can reverse the linked list as you're moving through it. I was actually stumped the entire day, and I ended up spending the entire day just contemplating if it was too late to change majors and stuff. I had to Google, I had to look up forums and stuff. I had to struggle through the code. I rewrote it a bunch of times. I submitted it a bunch of times before it was even accepted. It was actually just suffering. And then after that, I was able to get an actual working code. And we are now 2 out of 7 problems done. With arrays and linked lists, there are certain add-ons that we can implement into the existing data structures that makes them more efficient at what they do. But before we get to that, here are my final rankings for linked lists. I'll give them a 10 out of 10 for coolness because I think they're pretty cool. I'll give them an 8 out of 10 for difficulty. I had to spend an entire day of sitting down. The entire time I felt really stupid. And then lastly, I'll give them a 7 out of 10 for efficiency. There are definitely areas we can improve upon. Yo, is that the list of assignments you need to finish by tonight? What the hell? Yeah, man, I don't know. The teacher just kept giving these out, and then like, yeah, it just kept appearing. Well, it looks like you've got a stacks of homework there. A stack is a data structure that follows the principle of last in, first out. The last data that you add is the first data that you'll get out of it. Bro, the rain makes studying actually a bit more chill because data structures literally make me want to end it all. But you know, maybe I'm being a little bit dramatic. Stacks actually have 2 main operations: pushing an element to the top of the stack and then removing the element that is currently at the top of the stack. I used the same study strategy with stacks. The difficulty for me lies in visualizing its operations. You have to build up, push, pop, and all that from the start. It's still raining. It's going to be a very chill study day today. Stacks actually have a lot of real-world applications. Something as simple as when you write the text, it's pushed on top of the stack. If you click delete, you remove it from the stack. The problem I had to solve for stacks was called valid parenthesis. They'll give you a string which can only contain the following 3 brackets. You need to check the string to make sure that it's a valid string. A string is only valid if it has an opening bracket and every closing bracket must have a corresponding bracket of the same type. They must also be in the same correct order. Honestly, after reading that, I don't know if I spoke English or not. If you're confused too, it's not just you, because I went through the entire discussion forum and literally everyone was just talking about why it sucked, why the wording sucked, and why we should all just down. Honestly, I didn't know where to start at all, so then I just scrolled down and I looked at the first hint, and the first hint basically tells you to use a stack of characters, and that didn't mean shit. So then I moved down again to the second hint, and they told me as soon as you see an open bracket, you want to push it to a stack. That's when it starts to click. Firstly, you want to iterate through the string, and that means a simple for loop. Every time you encounter a closing bracket, you want to push it to a stack. And then the next time you find a ending bracket, you need to make sure that the ending bracket actually matches with the most recent bracket, because if it doesn't match, you're at the wrong order. And you have to do this for all 3 types of brackets. And then lastly, if anything goes wrong, you want to return false. If it went through the whole loop and nothing went wrong, you want to return true. Now that we were done with this problem, we can finally move on to the next data structure. Before we move on, here are my final rankings for stacks. 3 out of 10 for coolness. I don't think they're that cool. I'll give them a 8 out of 10 for efficiency. And then lastly, I'll give it a 8 out of 10 for difficulty, because you need to have a really good understanding of arrays and linked lists. Yo, is that the list of assignments you need to finish by tonight? What the hell? Yeah, man, I don't know. The teacher just kept giving these out, and then yeah, it just kept appearing on my desk. Well, it looks like you've got a
queues
of homework there. Queues are basically also like stacks, except it follows the principle of first in, first out, similarly to a line. The first person in the line is the first person to get what they want and then get out of the line. Queues have 2 main operations. On queue, adding a new element to the end of the line. DQ, which is removing the element that is currently at the front of the line. Queues also have lots of real-world applications. When you send your parents a loving message, it actually goes through a notification queue as it waits for the other messages to be delivered. So, if your parents never answer you or tell you how much they actually love you, it's most likely that the messages are still in the queue and that there's no other reason. I had to try and implement a queue using 2 stacks. When I sat down and read the question, I thought to myself, what the fuck? What does this even mean? When you try and look at the input and the example they give you, it just makes it more confusing. But what they're telling you to do is basically to implement all the functionalities of a queue using only the functionalities of a stack, and you're given 2 stacks maximum. I started off with creating 2 arrays, which I'll treat like stacks. There are also 4 functions we had to implement. The first function was pushing, which was the easiest function because in JavaScript, there's already a built-in method where you can just push an element to the end of the array. Our second function was pop. For a queue would mean removing the front element, but for a stack, pop means removing the last element, which basically means you have to make the last element of the stack the first element that you put in, which sounds kind of confusing, but you can actually do this very easily by simply just reversing the stack and then popping the last element out, which should now be the first element you add in. And then all you have to do is store that in a variable and then return it. For the third function, we had to do peek, which basically just tells you what the variable at the front is. You store it in a variable and then you just return that variable instead. The last function we had to implement is empty, which basically checks to see if the stack is empty or not. The easiest way to check if a stack is empty or not is by using the length function, which will allow you to see total length of the stack. If the length is more than 0, it is not empty and you return false. If the length is 0, it's empty and you just return true. After coding all the basic functionalities, I just clicked submit and the result was accepted after a few tries. There's always errors. From now on, the problems actually get much and much worse. My final rankings for queues are basically the same as what my rankings were for stacks. Let's move on to the next data structure. Currently, we're using add-ons to improve upon our existing data structures. But what if we take that a step further and straight up combine the best part of linked lists and arrays together? Well, that is exactly what the next data structure is, and it is quote-unquote designed to be fast to work with. Hash tables are a bit more complicated. Firstly, you generate an array of fixed size. Each slot within that array is referred to as a bucket. Data will come in a key-value pair. You use the key, put it through a hash function. It takes the key and it generates a number based on that key. And this number is actually the index of the value that you're going to store into the array with the buckets. This is day 3 of studying data structures and algorithms. Today, we're moving on to the harder ones. I am honestly terrified for my life right now. You can literally feel my shivering timber. Since HashTables utilizes the index-based approach, and since the array is already fixed size, this means that you can just insert and delete element, and you can also access the elements instantly using the index. The lead code problem I had to solve for HashTables was finding the longest subsequent string with unique characters. And this is where I learned of a problem-solving technique in coding, the sliding window. It does not sound cool, and it's also very confusing. What you do is you initialize a left variable and a right variable. It creates a range within your array or whatever. You can either increment the right to increase the range, or you can increment the left up to decrease the range. The way that you're doing this resembles the motion of a sliding window. So I got started off with using a set. It cannot contain the same value. It actually has a bunch of functions, and one of them is has, where it tells you if an element is already in it or not. And I just started off with initializing my left and right variable, the right being the length of the entire array, and that way I can iterate through them. From that point on, I just had to check if it's already included in the set, then I want to increase left up to where the repeated character is no longer within the range, or if it is not currently in the set, I want to add that in. And I also initialized a variable called max count, and I didn't even know this, but there's a function in JavaScript called math.max where it keeps track of the biggest value. Afterwards, I tested out the code and then it got accepted, and then I was officially done with this problem. Before we move on, here are my final rankings for HashTables. 10 out of 10 for coolness, designed to be fast to work with, is kind of cool. I'll give them a 100 out of 10 for difficulty. At least for me, I thought it was very difficult. And then lastly, I'll give them a 10 out of 10 for efficiency. It's the best of the best that we've studied so far. Now this is where the data structures start to get a bit more insane. It is called a tree because it basically resembles a tree, just upside down. It starts with a root node, and each node has child nodes and stuff. It follows a sort of hierarchy of data as it goes down, which makes it ordered and structured. The connection between the nodes is called edge. Now honestly, I can't make this up. I was using the same study strategy for trees, but I'm gonna be honest, I was really struggling. What is going on? It just feels really difficult for some reason. Like, you hear trees and you just think they're insane. Just put it in, bro. What is going on? And also, there's just so many things to cover. Oh, my computer just shut down. There's firstly what a basic tree is. There's also traversing through the tree, and there are like all these different algorithms and different methods of traversal. There are also many different types of trees. There's a binary tree where each node can only have 2 child nodes. There's a binary search tree where the right node is always larger and the left node is always smaller. And then you also have an AVL tree, which is a self-balancing tree. What does that even mean? I don't understand. I don't understand. By the end of my study session, I honestly did not feel like I understood trees at all. Thank you, God. Maybe I chose the wrong major, because honestly, what is going on with trees? Bro, I feel like Frank Heffley right now, bro. What is going on? For trees, I had to design a basic algorithm to traverse through the tree in order traversal. And in order traversal is basically when you go through every single left subtree before you go back to the root, and then you go to the right subtree, and you check that for every single node. Now, I actually found out that in order to implement tree traversals, you should take a recursive approach, which sounds very confusing, and it gets even worse. Recursion Recursion is a function that calls itself, except every single time it calls itself, it reduces itself down into a smaller version with the aim of reaching something called the base case. It reaches this point and then something happens and then everything happens all at once. Using recursion is actually good for tree traversal because you're essentially doing the same thing over and over again. You're just traveling to a left side or a right side. I started off with creating an array to store all of the value of the nodes, and then I created a function called traversal where it takes in a node. As long as this node is not null, which means that there's more values to it, then I'm going to call the function again, except I travel in the left side. Once it reached the point where it's null, I'm going to push it into the array that I created, and then I go to the right subtree instead. And you just keep repeating this until you've been through every single node in the tree and every single value is in the right order inside the array. It sounds extremely complicated. I didn't understand recursion. I don't think I understand recursion. I don't think I'll ever understand recursion. I clicked submit, everything worked. I was really tired already, so I was just done with it. But yeah, at this point, I thought trees were the hardest, but I was really wrong. Here are my final rankings for trees. 10 out of 10 for efficiency. We get it. At this point, it's efficient. I'll give it a 100 out of 10 for difficulty. I don't understand. And then I'll give them a 10 out of 10 for coolness. Nah, actually no. I'll give them a 5 out of 10 for coolness. We just ripped Mother Nature off. Graphs. Everything is graphs. Graphs are trees on steroids. That's it. I don't know how else I can describe them. Data in the graph is referred to as a vertex, and the connection between the data is still called an edge. Why is it called an edge? My study strategy for graphs were completely falling apart. I'm still taking notes, I'm still studying in spaced increments, but I don't understand it. Not only are there now different types of graphs, each vertex can be connected to however many other vertexes. In fact, it can even be connected to just itself. There are also so many other algorithms out there intended to traverse through the graphs. The edge itself can be weighed to where it has values. It can be directional. It can be completely random. The graphs itself can be cyclic. What is going on? This is where I must confess something. I did not solve a problem for graph. After I was done studying the theory for graph, I just did not have anything left in me. I'm sorry if you're looking forward to seeing me do graph problems. I'll just make another video where I just do a bunch of graph problems to make up for this one time. I'm so sorry. Here are my final rankings for graphs. 100 out of 10 for efficiency. Okay, can we stop now? I'll give it a 100 out of 10 for difficulty. What the fuck? And I'll give them a 100 out of 10. I don't know. I'll give them a 1 out of 10 for coolness because I hate them and I wish they never existed. Personally, I've had data structures on my to-do list for 4 months, but I've never ever gotten to it because I've always been so scared of what they are. If you're also putting data structures off, just sit down and get it over with, bro, and just continue to improve upon it. At least now, I'm finally done with studying them, and I can finally go to bed.